So this is one that the teacher, all these problems I did with the teacher that I was doing my student teaching with, but this page of problems are two that he had said were like really good AP type questions that they could ask. Now, like I mentioned, obviously not as seemingly big of a thing. I mean, I was doing this with him in like 2016, and I think in 2019 they revamped the test. So that's probably why, but I would say if you're going to put focus somewhere, this type of problem and the next type of problem is, pretty good place to do that. So, a man 6 feet tall walks at a rate of 5 feet per second toward a street light that is 15 feet above the ground. At what rate is the length of his shadow changing when he is 10 feet from the base of the light? So I'm going to use this little area up here to kind of draw out the situation that I have. So I've got my little street light here. And might not be the best depiction of a street light because it technically says from the base, I think, of the street light. Yeah, but like the base of the light would be like the light is on it, because technically like the way a normal street light looks, where it's like, the huge arm sticking out, you'd have to be looking from like where the light is coming down technically if you were doing a problem like this. So anyways, we're just going to pretend that the light is like on the pole basically directly. And so then this is 15 feet here from the ground. And our guy is 6 feet. And then essentially his shadow, I'm going to call S, would be over here. And essentially from the base of the light, that's like X, but this particular problem is going to be 10, but obviously he's walking. So I'm going to say generically this would be X here from the base of the light to where he is. But for our particular problem, we fill in like X and S. It's going to obviously end up actually having a value. So now we've got X and S are what I'm going to use. And then I've got dx dt and ds dt. So he's 10 feet from the base of the light, so that's going to be X. And then he walks at a rate of 5 feet per second toward the light, so that's my dx dt. Since technically that's going like toward, in my picture, it's going toward the left. It doesn't really matter as long as I declare which way is which, but the way I drew my picture, that's going to the left, so that's going to be negative.
So if you drew him going to the right, it would just be positive?
Yeah, basically. And then it'll just make your final answer is just going to shift a little bit based on the direction that you put on there. But essentially, he's going toward the light, and obviously, we're going to look at his shadow changing. So ultimately, I am finding, technically speaking, this ds dt value here. So it is a triangle, but technically speaking, I have more information than just what fits in a triangle, right? Like I have kind of like this big triangle looking at his shadow plus the distance he is from here. But then I also just have like this little triangle here. So this is where similar triangles are going to kind of come back into play in a different type problem than what we had yesterday. But another good kind of example of that. So I'm going to draw a triangle here. So this value is 15, and And then I'm going to kind of, not necessarily cut it in half, but I'm going to cut this triangle here, and I'm going to put a 6 there. And so then the distance between the street light and our guy is X, which again, we obviously have an actual value, but for the purpose of setting this up, we're going to call it X. And then between him and the like tip of his shadow, we're going to call S for shadow. So basically I'm looking at the little triangle and then the giant triangle. And so I can see that I have, the easiest part to see is the 6 over 15. So I'm going to have that first. Is equal to, then I need something else that I can do the ratio of. Well, the side over here of the little triangle is S, so I know that has to also go on top. And then over, well, the whole side of the big triangle would be X plus S. So I've got that there. And then basically I need to do, I always want to say be the pretzel because that's what we called it. Cross products. So I need to multiply across. So that's going to give me, when I distribute, it's going to give me a 6x plus 6s equals 15s. And then I'll subtract 6s over, and that's going to give me, I'm just going to write it under here, 6x equals 9s. So this is actually going to be the formula that I'm using because I care about the length of his shadow, not like the area or something like that we've been dealing with previously. So I didn't really have a formula that I just like knew to apply to this, so I had to kind of like find one. Yeah. So ultimately I know that I need to find ds dt. So there would be some benefit to going ahead and getting s by itself. And I could find S if I wanted to, like as far as like what his shadow is by using this information. But I don't need it because the S is going to go away just like volume and area did, where I didn't need like V and A. I just needed their derivatives. So I'm going to go ahead and divide by 9 so that I'll have 2/3 X is equal to S once I reduce it. And then I'll just take the derivative. So I would have ds dt is equal to 2/3 dx dt. So then just need to multiply that by -5. And so we end up with -10/3 feet per second. And essentially that would just tell me that like his shadow is basically like shrinking, more or less. Yeah, anyways. So then part B, at what rate is the tip of his shadow moving when he's 10 feet from the base of the light? So the tip of the shadow, to find that, I really just need the X plus S part of the bottom. Like nothing else is going to matter. So I basically just take, and now I have X plus S, and that's my formula that I'm using. I just need to take the derivative of that. So dx dt plus ds dt, which is -5 plus -10/3, and that's going to end up giving me, let me make this common denominator, 3, so -15/3 minus 10/3, so -25/3 feet per second is the rate at which the tip of his shadow is moving. So one of the big things to notice is like the difference here is in the first part A, he was technically standing still. In part B, he was moving. So that's kind of the difference in those two problems there. Anyways, that's it on that one. Next one. Sand is falling in a conical pile at the rate of 100 feet cubed per minute. Find the rate of change of the height, find the rate of change, I was supposed to say, if the height is 10 feet. Assume that the coarseness of the sand is such that the radius of the cone is always equal to its height. So basically, in both this one and the one above, they probably would have drawn a picture for you of what this like kind of looked like as far as like the situation, but anyways, we're doing it as if they didn't, because if you can do it without a picture, you can pretty much certainly do it with the picture. So I've got my conical pile here. I've got basically sand being poured onto the pile. And so I'm going to go ahead and set up the things that I'm finding, and then we'll go from there. So I know that I'm dealing with basically the volume of it, since it's like a cone and a pile of it. So V, and then for a cone, we've got R and H. And then dV dt, dr dt, and dH dt. So formula for volume of a cone, we had this yesterday, but V equals 1/3 pi r squared H. Now, they've told me that the radius is equal to the height. So if the height is 10 feet, that means the radius is also 10 feet. So I can go ahead and put in that information. And depending on what other information I have, I may do what I did yesterday where I swapped out one of the variables as well. And then volume, I know it's going to go away when I take the derivative, so I'm not even going to worry about that value. The volume is changing at 100 feet cubed per minute, so that's my dV dt. And then find the rate of change of the height of the pile, so that means I'm solving for dH dt. And I don't have a dr dt, so since I don't have that value, I'm probably going to need to basically change it to where I don't have r at all. So even though I have r, I don't have dr dt, so I'm probably going to need to substitute here for h, or let's say substitute h here instead is probably what's going to need to happen.
Since it says in the instructions that the radius of the cone is always equal to the height, could you change the formula to h cubed?
Yep.
Okay.
That's actually exactly what I would do, because if I had dr dt, or say I was solving for dr dt and I didn't have dH dt, then I would say, I would do it as r cubed. But since I have h and not dr, or I don't have dr dt, and I'm solving for dH dt, so yes, replacing it with h would be exactly right. So we would have V equals 1/3 pi h cubed. And so then we would just take the derivative at this point, and so we would have dV dt is 3 and the 1/3 are going to cancel, so pi h squared dH dt. And then if you want to get like to where DHDT is by itself, you can do that way, or you can go ahead and plug in numbers. But if I do it, DHDT is dVdt over pi h squared, and then just plug in, we have 100 divided by pi times 10 squared. Well, 10 squared and 100 obviously just cancel out, and so that means I'm left with 1 over pi for dHdt, and so then I just need to put units on it. That's just going to be feet per minute, so 1 over pi feet per minute. Let's see. I'll do number 3, and then I'm going to have you try number 4 and 5, and then I'll give you the answers to those ones tomorrow. And then tomorrow we'll do the book problems that go with this, a few of them, and then I'll give you a few more for practice out of the book as well. But I don't want to give you 5 without doing 3 because we haven't done anything with the sphere yet. So we have a spherical container is deflated such that its radius decreases at a constant rate of 10 centimeters per minute. At what rate must air be removed when the radius is 5 centimeters? So big things to note is that it says radius decreases here. So I'd make sure you're aware of that. I did not put the formula on here for you, but the volume of a sphere is 4/3 pi r squared, or sorry, r cubed, I mean for volume. So 4/3 pi r cubed. So that's another one of those formulas you'll want to be familiar with for the exam. I think we might have actually had that one in one of those maximizing problems the other day. Or minimizing, maximizing, whatever. So I basically just have V and R for this problem. So V, R, dV dt, and dr dt. So again, we aren't going to need volume. I can find it if I was so inclined. The radius is 5. Hello? Hey. Oh, okay. Okay. Yeah, we have a variety of ice cream because it was all donated. Beth has a few, like, popsicles, that she said that we could use that do not have dairy, but I don't know if that would help this problem or not for today. Yeah, the other option that we could do is if she's able to give us a like a brand that does work for him, because I'm sure there's other kids as well. Like I do something at church, and we have like essentially like an approved type of ice cream that we know that like these kids can have. So we always make it a point to have that, and I'm not opposed to doing that to, you know, for the kids to have allergies if I know. So maybe if we can ask her of that. This was just like very last minute. We decided this week to do it because we had all this leftover ice cream we needed to use. So, but yeah, no, perfect. Thank you so much. Bye. Okay, back to this problem. So then the RDT is it's decreasing at a rate of 10 centimeters per minute. So that would tell me probably needs a negative on there. And then basically solving for dv/dt. So derivative dv/dt equals the 3 and the denominator 3 cancel. So we got 4 pi r squared dr dt. And then just plug in, we got 4 pi times 5 squared times negative 10. And what was that? 25 and 4 is 100. Negative 10. Was that negative 1,000 pi or something like that? And then obviously units, centimeter cubed per minute for that one. Any questions on these so far? I didn't really talk about this, but obviously part of doing this is you can kind of do the unit analysis on this as well to make sure that like your units are making sense as you like go through. If you like actually stick the units on the numbers and stuff like that like you're given. Usually it's not an issue. I know I said like make sure you watch and ensure that like it's not going to ask you for, you know, like in centimeters cubed per second, like unless it tells you, like you assume you're sticking with it, but just make sure you watch for units on that, as that's like something that they could do on you is change that. Excuse me, the hiccups. Change that. So for the boat problem that I'm gonna have you try, and then the other one, the boat one is very similar to the ladder problem that we did. So just you can, if you need to refresh on that. And then the bottom one should be kind of similar to the problem that we just did up here as well. So we'll pause there. Like I said, we'll pick up I can give you the answers to these ones tomorrow, and then we'll pick up a few book problems, or just like a handful of them tomorrow. And so we should be able to wrap this up basically by then.